Good morning and good afternoon, everyone. Welcome to today's webinar. Thank you all for joining us today. My name is Maike Diekmann. I'm the Technical Support Manager at Thorlabs Germany, and I will be the moderator for today. Today's webinar will be the first installment in our light characterization series. Today we will learn about the various options for power and energy meters, their specifications and characteristics, and some best practices to consider for your application. It is my pleasure to announce our speaker for today, Manfred Gonnert, the head of the Light Detection and Analysis Technology Department here at Thorlabs Germany. Manfred studied electrical engineering at the University of Applied Sciences in Munich before joining our company back in 1991. He began his work in production, and from 2002 onwards, his responsibilities evolved to include the design of power and energy meters, as well as related products. He began leading the Light Detection and Analysis group in 2018, where he continues to grow and enhance this product line. He will give a 45-minute presentation followed by a Q&A session. You're welcome to submit any questions throughout the presentation. To do so, just click on the Q&A button on the top right of the screen. Now, with that, it's my pleasure to turn it over to Manfred.
Maike, thanks for the introduction, and yeah, let's start. We'll cover a lot of topics, and so let's just jump in. As first, we want to talk about what is light in general. So light is known as an electromagnetic radiation that ranges from gamma rays to radio waves. Within the spectrum, our range of interest is the detection of laser radiation that extends from deep UV, or also called vacuum UV or UVC, up to tens of microns. This is far infrared with transition to terahertz waves. So light can also be seen as particles, the photons, that don't have a mass or a charge, but carry an amount of energy. Let's pick here a photon out of the violet range that oscillates with a certain frequency and propagates with the speed of light. As for every moving wave, the wavelength can be calculated by dividing the propagation speed by the oscillating frequency. The usual term for the photon propagation in laser measurement is the wavelength in nanometer or micrometer. In spectroscopy, often the reciprocal value, the wave number in centimeter to the -1 is used. The frequency value in terahertz is often taken in telecommunication networks. The frequency here gives simpler numbers for the carrier frequencies and the channel spacing. In quantum physics experiments, mostly the photon energy in electron volts is the key parameter for the characterization. This can be calculated by the Planck constant times the frequency. The photon energy is also the key to being able to measure light. To summarize, it is important to know that each photon carries energy that is larger the shorter the wavelength is. So light can be measured from two perspectives. The first is the radiometry that takes into account the entire spectral range without weighting. The measurements are radiant flux in watts and the irradiance in watt per square meter. Radiometric units are used when measuring laser radiation. With photometry, shown on the right side, the measured amount of radiation corresponds to the human visual behavior. The radiometry equivalent measurements are luminance flux in lumen and the illuminance in lux. Also, a unit that is in use for the illuminance is the foot candle. Let's look what components make an optical power or energy meter. So first part is the sensor that is responsible for the photon to electron conversion. The signal from the sensor must be digitized and processed in the electronics. Finally, the measurement value can be either shown on the meter display or in a PC graphical user interface. To get reliable measurement results, both sensor and electronics need to be calibrated. Let's start with the power meter electronics part, as this is quickly to explain. First, the small currents and voltages that can start in the nanoampere range or microvolt range are amplified in order to get a reasonable voltage level. This includes also a multi-level ranging over several decades. In the next step, the signal gets filtered for unwanted noise or fluctuations and afterwards digitized to the microcontroller. In this section, the power level is calculated taking the sensor calibration values into account. Last point is to bringing the measured value to a display. The electronics gets calibrated by applying well-defined currents and voltages for each measurement range. The accuracy of the electronics outperforms the system accuracy by far, so it is enough to focus on the sensor accuracy when looking on the complete power meter accuracy or power measurement accuracy. As next, I will show how a semiconductor or photodiode power sensor works. Photodiodes usually are built as PN junction with an intrinsic intermediate layer, the so-called depletion region or depletion zone. When now photons hit this layer, electrons and holes are excited and directed to the corresponding zones. This leads to a flow of electrical current. To characterize a photodiode, the quantum efficiency, in this case, it's more the internal quantum efficiency, is usually used to determine the performance of a photodiode. The responsivity of a photodiode, this is the size we are interested in most, corresponds to the external quantum efficiency at which all photons that reach the diode surface are used for the calculation, including those that don't reach this carrier zone because of reflection or absorption in the upper layers. The reflectivity is defined through the current flow by the incident power. To name the benefits of photodiodes, they respond very fast with nanosecond speed. They are sensitive down to sub-picowatt range. They are linear over some 8 decades, are low noise, have a low dark current, and can have a very small footprint in various packages like different TO cans, single chips, or ceramic packaging that is often used as well. So to the limitations as downsides can be mentioned that the early saturation at some single-digit milliwatts. This is the point after the response gets nonlinear. The spectral range is limited due to the diode material and furthermore strongly nonlinear. There is also an increased temperature dependency at the edges from the useful spectrum. The active area size is limited to some 18 by 18 millimeters. Further, the price increases exponentially with the area size and also with the wavelength. As last, and especially in power meter applications where the photodiode for noise reasons are operated unbiased, the amplifier circuit slows down the response speed. To have the ability to measure higher power levels than the saturation level, an attenuation of the incident beam is mandatory. This can be achieved by neutral density filters or integrating spheres. Let's have a closer look to the filters and start with reflective filters. These are made of a fused silica substrate to be transmissive in the UV. The entrance side is diffused in order to broaden the beam while the beam passes the filter, and the backside is the actual filter layer that is made by deposited metals. The used filters show transmission values between 0.1 and 20%. The transmission is very linear over the spectral operating range. When we come to absorptive filters, these absorptive filters are made of filter glass where the attenuation happens within the glass while the beam passes through. Advantage of these filters is that they don't show interference or polarization effects. Therefore, they are better suited for the IR wavelengths compared to the reflective ones. Disadvantage of these filters is the spectral nonlinearity, you can see here, and the reflective surface that makes Fresnel reflections, and the temperature dependency. So when this filter gets hot, it gets thicker and therefore it attenuates more. It's just a small portion, but it influences the measurement. And as last attenuator for a photodiode, we can use an integrating sphere. These spheres' inner surface are made of diffuse reflective materials. This can be either sintered Teflon for the UV to IR range and gold for the NIR to far infrared range. The incident light homogeneously distributes over the surface by multiple reflections. At the detector port, a small portion of this light is picked up and used for the measurement. Then let's come to the most important part for a photodiode power sensor, the photodiode itself. This is the key element that generates the current that is proportional to the incident light. Photodiodes have a limited spectral range that is dependent from the materials they are made of. Here highlighted are the mostly used material, that is silicon for the UV to NIR range, and germanium or indium gallium arsenide for the near-infrared to infrared wavelength range. And since we already have seen, we have a couple of spectral nonlinear parts, so there is a sensor-specific and type-specific calibration for each sensor necessary. I will show here the calibration principle. The setup for the calibration of a photodiode sensor that must be done over the whole whole spectral range the diode can work consists of a white light source, a monochromator that splits up the light to its spectral components. Further, you will need an optical chopper and a lock-in amplifier to measure the photocurrent. In the first run, the power for each wavelength point is recorded with an externally calibrated reference standard. And afterwards, when you know the power from the monochromator, the same power levels are radiated upon the sensor to calibrate. The result enables the calculation of the spectral responsivity. Next, we will come to the thermal sensors, where there will be an intermediate step in the conversion from photon to electron. The photon energy first gets converted to a thermal energy. Once the photon energy is converted to heat, it is necessary to measure this heat flow. This can be done using the thermoelectrical effect. Metals or alloys, when get heated on one end, release electrons in direction to the colder side, as long as there is a temperature gradient. This phenomenon detected by Seebeck, therefore the thermoelectrical effect is also called the Seebeck effect, varies from metal to metal. Since the effect is not well measurable in one piece of metal, many materials got characterized and ordered in a thermoelectric voltage series in reference to platinum. With that knowledge, it is possible to build thermocouples that generate a voltage when heated on their connection point, the hot junction. In our example, we are using iron that generates less electrons and nickel that generates more electrons, reference to platinum. When now heating the connection between iron and nickel, and assuming that the cold junctions are at the same temperature level, a predictable voltage per Kelvin is generated. So to get a real thermal sensor, connecting multiple of such thermoelectric generators in a row increases the voltage to a reasonable measurable level. The first thermal sensor setup here shows a radial setup where the couples are arranged circular around the incident area. The heat dissipation horizontally moves from the center to the outside. The second arrangement is a matrix style with incidence on a top layer and a vertical heat flow to the heatsink. The thermal sensors respond in an exponential function, like charging a capacitor. The key parameter here is the time constant. This is the time when 33% of the final value have been reached. That time constant characterizes the response speed and is also used to perform a measurement prediction, allowing to display the power prior the voltage has finally settled. So you can see here the red curve. Already here you know how high the power level will be. That is just after 5 time constants, nearly 99%. So now let's see to energy sensors. Also, energy sensors are using the photon to thermal energy conversion. We will see how to get to electrons for this here. A pyroelectric sensor acts like a capacitor that is electrically charged by thermal flux. It contains a crystal from pyroelectric material embedded between two electrodes. Pyroelectric crystals include dipoles that are randomly polarized, so there is a certain so-called spontaneous polarization at constant temperature. When now a light pulse hits the active area, the dipoles change the polarization and absorb or release electrons while the heat wave passes through. Try to show it again here. So you have a charging and a decharging. Important to say that pyroelectric sensors only work with alternating light. On the other hand, they can detect the shortest pulses as long as the energy within the pulse is high enough for the detection limit of the sensor. The maximum detectable repetition rates, that is in some tens of kilohertz, is dependent on the sensor size, the coating of the sensor, and the load resistance. Here are two examples for the recovery time of such sensors. On the left side, you can see it recovers after 200 microseconds, which results in a repetition rate of 5 kilohertz. And the right one is more or less with a recovery time of 9 seconds. So you can measure up to some hertz. To complete the thermal detectors for the use as a measurement head, they need an absorption coating that can collect the incident heat. Black layers show here the flattest absorption from UV to terahertz. When higher durability is needed, ceramic coatings are the best choice. For highest speed, metal coatings can be used as well. Especially for thermal power sensors, a sufficient heat management is mandatory. It is important to keep a certain temperature gradient between the active area where the beam enters and the heatsink. Depending on the application, convection, water, or fan cooling can be used here. For measuring the lowest power levels with thermal sensors, it is important to shield the sensitive area from black body radiation, because the sensors react on every heat source. So if you move in front of the sensor, it will pick up your radiation as well. Further, there shouldn't be any air vents or ambient temperature changes. As advantages for thermal sensors are the robustness against high power levels and energy levels, the spectral flatness, especially for the black coating, and the possible large active areas that can be up to 50 millimeters. The downsides, the drawbacks here are the reduced sensitivity against a photodiode sensor, and also the noise is larger than a photodiode sensor. The low speed response, zero drift for longer exposure times, and given by the heat sinks, the larger footprint. So to calibrate a thermal sensor, this is done usually in 2 steps. For the spectral calibration or spectral correction, the absorbance of the coating gets characterized with a spectrometer. The actual calibration against an externally calibrated reference standard is usually done with a 1064 nanometer continuous wave laser for the power sensors, or a pulsed laser also at 1064 nanometer for the energy sensors. Here a short summary. For continuous wave lasers, only photodiodes and thermal sensors are working. When it comes to higher peak power or pulse lasers, the photodiode sensors would fail, or damaged thermal power or pyroelectric sensors can be used. Now it's time to get into practical examples and applications. The first step is obvious. You have to choose an appropriate sensor and connect it to the meter. Prior to starting a measurement, there are some initial settings you have to care about. The first and most important one is the spectral correction. This is mandatory to get reliable measurement results. When having a laser that usually emits at one wavelength, it is rather simple. You just have to enter the laser wavelength to the meter, and the correction value will be taken from the sensor response curve. It gets a bit more complicated when using a broadband light source, like the here shown white LED. In this case, it is necessary to calculate an effective wavelength and therefore an effective responsivity from the light spectrum and the sensor responsivity. The here shown power meter, the PM400, does the job for you. You can upload light spectra to the instrument in comma-separated lists and choose those for the wavelength correction in the wavelength dialog. Next topic is the zeroing. You should launch this wizard prior to your measurement, especially if you don't work in a dark environment. Please be here aware that the zeroing doesn't help when the ambient light changes during the measurement. In that case, it is better to shield the beam from ambient light. Also, when measuring very low power levels with thermal sensors, zeroing becomes more relevant, since there is often a slightly offset due to the ambient temperature conditions. So when measuring continuous wave power levels, the range setting can remain in auto-ranging. It's indicated by these arrows. For monitoring the analog output or measuring pulsed or modulated systems, it is advisable to change to manual ranging. As a hint here, you can check the measurement range saturation in the bar graph display that updates faster than the reading above it. Last setting is here the bandwidth adjustment that applies to the photodiode input. Noisy readings can be smoothed with a 16 Hz low-pass filter. In the next couple of slides, we want to see how angled or divergent beams can influence the measurement. As first exercise, the sensors are tested with collimated beams under normal incidence. Collimated beams can be found at helium-neon lasers. This is a classical collimated beam, and diode lasers with a suitable optics. The result here is not surprising. In all three examples, the measurement value is correct. Since this is the same condition like the sensors have been calibrated. To avoid back reflections, however, directly to the laser, especially for helium-neon lasers, they get completely out of stabilization if you shine back to the laser. The sensor can be positioned in a slight 1 to 2 degree angle. As next example, we want to see what happens for larger angles of incidence. Here we watch the beams, and in both filter setups, we are measuring two low power levels. In the upper example, the reflective filter widens the beam, widens the spot, and the active area is missed by a fraction of the light. In the middle case, the Fresnel reflection gets increased by its angle dependency. The integrating sphere is widely independent from the angle of incidence unless the photodiode port is not directly hit by the incoming beam. Therefore, and this is just a schematics how the integrating sphere works, the detector port is recessed to the input port so that it can accept wider angles of incidence. The next observations we want to make is the behavior of sensors with divergent beams. Divergent rays are emitted by diode lasers, LEDs, or fiber tips. So with photodiode sensors, care must be taken to not overfill the active surface of the photodiode. Here you also have to be aware that the sensitive area of the photodiode sits a bit recessed behind the filter. So even if your beam fits inside the aperture or inside the filter, it can diverge so that the photodiode gets overfilled. In general, the same problems as for high angle of incidence apply also to the measurement results. We have in both filter combinations, we measure too low power. Here again, the integrating sphere is the best choice for divergent beams. It will show the correct value upon to a large incidence angle or divergence angle. Here an overview of the angle dependency for different sensors from top to bottom. Best results deliver thermal sensors. They nearly don't show any angle dependency due to the surface with the high absorbance. Next best options, as we already seen it in the examples before, is the integrating sphere that can handle angles up to ±40 degrees. Photodiodes without filter work well up to ±20 degrees. But here you have to take care if the photodiode is protected by a glass window. This can also decrease the acceptance for angles of incidence. Photodiodes with filters should be limited to a ±5% working range. Let's have a closer look to a specific application. Power measurement at microscope, especially if you want to measure the power at the objective plane. Here, usually the light is strongly divergent, given by the high NA of the objective. Here, a warning ahead, don't focus on the active area of the photodiode when measuring the power at that spot. The diode could take damage by the high power density. Integrating sphere or standard thermal sensors are usually ruled out for reasons of space. On the right side, a standard sensor with ND filter is used. The refraction at the transition from the filter, the slow medium, to the air gap as a fast medium leads to an even greater expansion of the beam, so that less light hits the active surface of the sensor. So what can we do to solve this problem? First and obvious thing, let's increase the active area. Next one is to get rid of this air gap with the low refraction index. This is done by filling the gap with a translucent gel with the same refraction index than the ND filter. Additionally, we want to have an easily cleanable surface for the use with immersion fluids. The outcome here was our S170C sensor that has the shape of a standard microscope slide. To summarize here, take care when measuring divergent beams or with strong deviations from a perpendicular incidence, especially when using a photodiode sensor with ND filter. So the next chapter will deal with the measurement of pulsed or modulated radiation. First advice here is when measuring alternating signals, turn off the auto-ranging and choose a measurement range that is larger than the expected peak power level. Check via the analog output whether the chosen measurement range will work. For lower frequency, watching the bar graph might be sufficient. When using the analog output, switch the bandwidth to the high setting to see the signal and also see whether the measurement range gets saturated. Set it to low when you can't read the measurement values because they fluctuate. In our first example, we want to start with a sinusoidal signal as it comes when using an optical chopper wheel at a sufficient frequency. The sampling interval is 4 measurements per millisecond. This example with 1 kilohertz gives a reliable average value. So all sample points can well be on the pulse shape. Now we have a look at a rectangular modulated light source. We sample again with 4 kilohertz. The measurements are well distributed between the roofs and the valleys of the waveform, and therefore the results also gives a reliable average power reading. We can also measure such a signal with the bandwidth low settings. And this example should demonstrate that this filtering can be applied in unfortunate conditions of getting unstable power readings. The short pass widely flattens the signal so that the sampling points are nearly on a horizontal level, and of course the average power measurement is fine. So now to the more complicated cases. When it comes to smaller duty cycles, the probability of catching the pulse peaks decreases and the measurement value gets a bit too low. Additionally, and in this example with 1% duty cycle demonstrates it very well, the measurement results are in an unfortunate segment of the measurement range. So the measurement range here must be greater than 1 watt to catch the peaks, and the signal is 10 milliwatt. The accuracy of any measurement device gets down when coming to the low end of the measurement range. So we want to demonstrate the solution against this here, and this is to increase the sampling rate, and that's what we did on our latest USB power and energy meter. This can take up to 100 kilosamples per second and can so dissolve the pulses from some 20 microseconds pulse width. Further, it features an oscilloscope-like representation with the ability to calculate the pulse energy. Another benefit is the direct measurement of the peak power so that the measurement range can be used optimally. Also, there is a convenient auto set function with a peak finder and an automatic trigger level set. So when it comes to short pulses as emitted from femtosecond lasers, the measurement of the average power with thermal sensors or integrating spheres can still be done. However, when wanting to measure directly the pulse energy of a Q-switched laser, pyroelectric energy sensors are the best choice. Prior to starting an energy measurement, the expected pulses should be estimated to choose the right sensor due to the repetition rate and the damage threshold. Energy measurement works only in manual ranging. Therefore, set the measurement range to a value according to the expected pulse energy and a trigger level of approximately 50% of the expected pulse energy. The sensor then will directly give a reading of each pulse's energy value. And you can also calculate the average power of it, or the meter does this for you by multiplying the energy with the frequency. You can also measure the energy with thermal sensors. In this case, it can only measure single shot energy pulses. And hereby the time constant of the pulse must be much shorter than the time constant of the sensor. And the pulse energy can then be calculated by integrating the power response. So as a guide, an overview chart that shows the best sensor choice for modulated or pulsed laser beams. The pyroelectric sensor rules out due to its sensitivity or repetition rate in these first three examples. In general, I'd say it is pretty difficult to give a general recommendation. There are always exceptions that require careful considerations. So, for example, you can also measure 100 watt power with sufficient large integrating sphere, and you can measure very low power levels with the thermal sensor. So this should give a bit of a guidance here. So the next slides, irradiance and beam position measurement will be demonstrated. So when the power measurement is related to an area of illumination, one speaks of irradiance. This kind of measurements can be perfectly used when the light source emits a much larger than the sensor area. Most obvious example here is to measure the irradiance of sunlight. For example, to characterize solar panels. Also knowing the exact irradiance for UV curing tasks or illumination of biological probes is very important. How does it work? The simplest way to measure the irradiance is to overfill a standard sensor. The light distribution should there be homogeneously over the size of the sensor aperture. The power meter electronics automatically takes the sensor aperture to calculate the irradiance. When the homogeneity of the light source cannot be guaranteed, it is necessary to attach a defined aperture where you can be sure that the light is homogeneous, can be put in front of the sensor. The size of the aperture can be entered in the measurement settings, and the irradiance will be calculated and displayed. Another application is to measure the irradiance or the power density of a laser beam. Hereby, the beam must be smaller than the active area, and the beam diameter of the mostly Gaussian beam must be known. Again, enter the beam shape, circular, type, Gaussian, and the diameter, example 3 millimeters, and the irradiance value will be calculated and displayed. Here to note is that the irradiance of a Gaussian beam has a factor of 2 compared to a homogeneous flat top beam. Because it's in the middle of the beam, it has a much higher irradiance than over the full area. As a last power measurement related application, I want to demonstrate here the beam position measurement with thermal sensors. For that task, the thermal disk or element is divided in 4 independent quadrants. However, the cover layer on top of it with the absorber surface goes over all 4 quadrants. When a laser beam now hits the sensor, the absorbed heat will dissipate through all 4 quadrants. Summing up all 4 voltages give here the power measurement. Depending on where the beam, which is, by the way, is independent from its size, hits, its position can be calculated using the 4 quadrant voltages by the shown formulas. The result is reproducible so that relative accuracy of down to 10 microns can be achieved. Also, the speed of the sensor is sufficient for automated setups. The main application here is the alignment of infrared laser beams. One of our power and position sensors fits within the 30mm cage system and can be used from approximately 10 milliwatt laser power. So, in addition to daily lab and field use, our meters are perfect for integration in automated measurement setups, also in industrial environment. In addition to the option of logging and saving data in the device, various computer interfaces like USB, RS232, Ethernet, or Bluetooth are available. The free power meter software is a very good starting point for acquiring measurement values from multiple power meter or temperature sensor devices. It further features some useful tools like a wizard to performing user calibrations, calculating tools, or firmware updates and supporting temperature probes. It further comes with all that is needed to integrate the meter into larger measurement systems. To program own applications, the accompanying driver set can be used. There are examples attached to allow a quick progress. It is also possible to implement the meters as USB test and measurement, USB TMC devices, and use the standardized SCPI command language. It works also on other operating systems than Windows. So Thorlabs offers a really broad portfolio of power and energy sensors and suitable measurement electronics for field and lab and factory floor. If you cannot find the right meter or sensor for your application, or if you need modifications, don't hesitate to contact our technical support. Visit our website for all technical specifications, further information, and insights. So that's been it for today.
Thank you very much for the great presentation. We have some time for questions. So any questions, you're welcome to keep posting them in the Q&A chat. Let's start with the first one here. If you have a higher power, is it better to rely on the sensor ID filter or to use a laser pickoff that picks off a small amount of laser power?
Yeah, that's a good question. Depends, of course, on the power level. In general, especially absorptive filters really have a low, can handle a low power density. Reflective filters can have a bit more, but in general don't exceed the power level of 1 watt. So as a rule of thumb. So if the level is higher, yeah, take a pickup.
Thank you. Any additional questions? So I see one question here. What's the best way to measure the power of a broadband light source at a specific wavelength? For example, 670 nanometers.
So you want, if I understand it right, you only want to pick the 670 nanometers of this broadband light source.
I think that's what they meant.
Okay. This can, since every power sensor sees the full spectrum, you would have to have a laser line or line filter that takes only this specific wavelength. Otherwise, it's not possible with a power sensor.
Okay, thank you. Another question would be if you have some advice for what we can do if our thermal sensor is drifting.
Okay. This usually happens if the thermal management is not pretty good. That means the heat sink of the sensor heats more, so you can't keep this temperature gradient I talked about with this Seebeck thermocouples. Depending here a little bit again on the power level. So for very small power levels, it's good to house the whole sensor that you don't have any air ventilations. For high power levels, you might need a better heat transfer or a better heat sink. In this case, maybe a fan cooling or water cooling.
Okay, thank you. And then maybe a last question that I can see here, if you could explain the difference between how the calibration of a photodiode works compared to the calibration of a thermosensor.
Okay, for the photodiode, we don't use a laser light to calibrate it. It is done with this monochromator setup that splits this broadband white light source into its spectral components. So we have a monochromatic light with a specific bandwidth. It's not just this laser line as for a 1064 nanometer laser. It's a bit broader, in maybe 2 to 4 nanometers. And the other, or the most important part, is that you have to calibrate the photodiode really in equidistant wavelength steps to get the complete responsivity curve under calibration. For thermal sensors, you are using a laser to calibrate. And this is mostly sufficient to do it on one wavelength. Then you know the absorption of the layer, that absorber material. When you really want a specific wavelength, then you don't rely on the absorption. The calibration could also be done at other wavelengths, what gives then a better result. Really important is to have for both calibrations a reference standard that has been calibrated at any external national body like NIST, or in Germany here the PTB.
Okay, thank you. I don't see any further questions at the moment, so I would conclude the Q&A. If any further questions come up, you're welcome to contact us anytime. You can check out our contact page on our website. Depending on your location, your local tech support is usually the best place to reach out. Any questions will definitely be forwarded to us if there's anything specific to this talk. So with that, thanks again, Manfred, for the great presentation and for answering the questions. And have a good day, everybody. Bye-bye.
Bye-bye. Thank you all.